Okay, let's start. We were here previously. Uh, just a moment. So, binding of quantifiers variables. We are in the topic of quantifier, and binding of variable for the quantifier is if you have the mathematical equation uh, and if you are using a quantifier, either universal, either existential. So there are three concepts: bound, free, and the scope. In a mathematical equation, if you are using a variable and and quantifier you are using with some variable, then it means that that quantifier is bound to that variable. If you are using a quantifier with a variable, then it means that quantifier is bound to that variable. If any variable if for any variable you are not using any quantifier, then it means that that variable is free. Simple. If you are using a quantifier, that variable is bound. If you are not using a quantifier with a variable, then that variable is free. And but for free, you also have this another uh, sentence for its little bit definition. So if a variable is not bound by a quantifier, so that variable would call free. That is one thing. Or if not, if value not set to, if variable not set to a particular value, if any variable not set to a particular value, which means if no any value is given to some variable in terms of the domain value, then that variable would also be called free. And scope is what? That if you have the equation, for example, if that equation have three parts, for example, and here you are using some variable or some quantifier, and here in this part you are not using any quantifier, and here you are using some quantifier again in that equation, then the scope of this quantifier is only this part of the equation. This would not be the portion where your quantifier has some effect or influence. Similarly, at this part of the equation, this would be called the scope of this quantifier. Either it is universal, either it is existential. So these are the three terms. Now, this is an example. If we have this statement, there exists x plus y is equal to 1, then this existential quantifier is with variable x. So, in this notation, in this propositional function, we have two variables, x and y, but x is bound, and as we don't have any quantifier with this y, so y is not bound. Y is free. And as we don't have any value set for this propositional function, because here in this question you will not see that any value is given to these variables, especially to y. So there is no any value. This is second sentence that we saw in the definition. But initially you have to see that there is some quantifier with that variable or not. So there is no any quantifier with this variable. So that's why you can say that the y is free. Similarly, if you have this mathematical equation in which it is starting from here and this portion is ending here, so this is one portion of the equation, and after disjunction you have this portion also. So now we have to discuss the scope of this variable. So scope of the quantifier, not the variable. So this there exists, is used with x, and x is here and x is here, but starting, this is the starting parenthesis and ending. So from this portion we know that this quantifier has a scope only in this part of the equation. Scope means lifetime. From which time to what time that variable is existing. And then this quantifier for every has a scope only in this part. By the way, it is written here, read it yourself, but I have explained. So then you can now read. Then logical equivalences. So we are almost studying the previous things that you saw in chapter 1, but now we are seeing these things with the quantifiers and the predicates. Logical equivalences within the quantifiers. So previously you saw that how you can say that these different propositional functions or propositions are logical to each other. There are two ways. First is that you can calculate the truth table of those two propositions, and if the resultant values of the truth tables that you got, if their resultant values are similar, then you can say that those compound propositions or those propositions are equivalent, logically equivalent to each other. And the second way is you can take first proposition, and by using the method of replacement of statements with some other statements, you can finally reach at proposition 2, and then you can say they are logically equivalent. So here, logical equivalence, we know that if we have any statement and we have predicates and quantifiers in it. What is predicate? For? What is predicate? For seal? For C? No. What is predicate? We saw the definition of predicate just in previous slides, in the previous slides. If I will ask quantifiers, then maybe you will say, okay, these are the quantifiers. But what is predicate? Say it slowly, then maybe I will understand. I am not understanding what you are saying. The same expecting. The same expecting. The same expecting. What it means? Same expecting. It means maybe you are expecting the same thing. But this is not the answer of the question. Previously in some slide when we were seeing any sentence, by the way, here this P of X is predicate, this Q of X is predicate, this R of X is predicate, which we use to represent some portion of the sentence. And what portion of the sentence? Which is starting from the verb up to the end of that remaining sentence. For example, in some previous slide, this is the wastage of time now. I only have 35 minutes. Here maybe, no, this is quantify. Here when X is greater than 3, then I told you that this X is the variable. And is greater than 3 is the predicate. And for that predicate, to represent that sentence, we can use P of X. And now what is the meaning of this P of X? X and the P is this one is greater than 3. So X is greater than 3. Anyhow. So if there is a statement in which you have the predicates and the quantifiers, and if you want to see that those statements are logical equivalent, then what is the condition? They would be a logical equivalent if and only if they have the same truth value. If, for example, if you have two statements in your question, then the truth values for the statement 1 and the truth values for the statement 2 must be equal. And how you can calculate the truth values? Through truth table, yes. By evaluating the true false values in the truth table, then you have the truth values. And you can represent the two statements if they are logically equivalent like this, that you already know. This symbol, what is this symbol? Horizontal 3 lines is for the logical equivalence. Now, this is an example, but it is theoretically not. And in this example, we are showing that the two statements are logical equivalent just with theoretical discussion, not by truth table, not by replacement of statements. But actually, this is something, anyhow, show that this one and this one are logical equivalent. And the domain is not given, but only said that the same domain is used throughout. So it means that you can suppose any domain for these two statements. So here, this question is very much theoretical, and the answer is already there in the question. For example, to prove that these two statements are logical, only for this question, you have to take first statement and you have to evaluate its truth value, not by truth table, just theoretically. You can calculate some truth value, but then it is not complete. The information is not complete. You will take this first statement and then you will discuss that what it is and what is the truth value for this one. And then you will start with this one through supposition. You will suppose something by taking this first statement, and then you will discuss something. And finally, you will reach at the truth value of this statement, which would be, or you can say, oh, or you can say you will start with this statement 1 by supposing something, and you will reach at this statement 2 in the first step. Yes. And similarly, then you will start with this statement 2 as a supposition, and then you will discuss something, and then you will reach at the statement 1. And then if it will happen, then finally you will say that both these two statements are equal. So this is the approach here, which is discussed here. So, okay, the actual discussion is starting from here. Here it is just said that how you can do that. So first we are taking this statement 1, and we are supposing that this for every x, p of x and q of x is true. So this is your supposition. So you are supposing that this for every x, p of x and q of x is true. And what it is something, for example, p of x, or you can say a and b, and conjunction is there. And when there is a conjunction, you can take any value for the domain, maybe a. You can take any value for x, a, b, c, d, whatever. When both will be true, only then you will get this whole p of x and q of x true. Only then. This is true or not? Yeah. Because the conjunction is there. Because the conjunction is there. So if you will just read it, this is the story now. So here we are taking some value for the x. If A is in the domain, a value in the domain, then P of A and Q of A is true. If you will take some value of the domain, then this conjunction would be true because we have supposed that it is true for all x. We have already supposed, so you have to go with your supposition. So if it is true, then this would be true, P of A and Q of A. Which also means that individually this P of A is true and individually this QA is true, and then conjunction is making the whole thing true. So which is also means that P of A is true and the Q of A is true. For every element of the domain, whatever the value you will take here for the x from the domain, because the domain is same for these two statements, then you will get it P of A true, Q of A true for all elements of x. So you can say for all, if P of A and Q of A will be true for all elements of S, then you can write it separately. Like P of X would be true for all elements of X, and Q of X would be true for all elements of X. For every element, you can say separately, which is basically, so it, and how you will get, so I can say that individually, if this P of X would be true for all X entries, and individually Q of X would be true for all entries of X, and if you will make the conjunction, if both of these parts would be true, then after making conjunction, you will get again the true value, which is this second statement. So you are reaching at this second statement by theoretical discussion. By theoretical discussion. And similarly, you are supposing the second part. The second part is for every x p of x and for every x q of x. Now you have to suppose that this is true. So if it is true, and when it would be true, you can discuss by yourself. You don't have to rely on these words. So from this equation, we know that for all xp, so this is true. How this whole equation will be true? Because you have supposed that this is true. But now discuss it logically. If both parts will be true, only then due to that conjunction, you will get this whole true. So now what is the method? You can say, okay, for any value of the domain, maybe you are taking A, and then you can say that this P of A would be true, this Q of A would be true. Or you can say, and then you can use the conjunction between them that this would be true for any value. And when you will use for any value, then you can finally use that this portion and this portion, this would be true for all x. For all x, which is the right hand side, which is basically the right hand side. And then finally, you can simply say that this one statement is equal to the second statement, logical equal. So this is just a theoretical discussion. And from these statements, these are not complex statements, you can easily identify that if you are supposing it true, then how you are getting this true, you can discuss that thing. And similarly, you can take the other statement and you can discuss that thing. Now, the next, when the last 15 minutes will remain from the lecture, then kindly inform me, then we will go for the quiz, okay? Last 15 minutes. Starts now? I don't think so. Last 15 minutes will remain, okay? I think, yeah, from the full time, you have the two classes, okay? So I think it will end on 2:20. I think. I don't know. So the first lecture would be at 1:35, and the second will start from 1:40 to 2:15, so 2:20. Okay, so we will start quiz at 2. Okay, it will take only 5 minutes, but I will give you 15 minutes. Nested quantified expressions. One more thing. This course, this is the starting. This is the first chapter that you are going through with. This is a wonderful subject, by the way. I have seen the contents now, but I have to prepare the slides. But due to less timing, I will skip some topics. Maybe I have announced it already, I don't know. Otherwise, I will not be able to complete this course. And being a head of some committee, I removed one CO from the contents already. So I got the approval. That is a good news. So now CO5 is now removed, which is about some algorithms. You will see that CO, similar CO in another course, and that course is analysis and design of algorithm. You will see that CO which you have here as a CO5. The same CO is existing in another course, analysis and design of algorithm, at number 2, CO2. In that course, that is CO2, and here it is CO5. So when you will start that course algorithm, first you will learn how you can calculate the complexity of any algorithm using asymptotic analysis. That is something mathematical. So that's why it is the part of this discrete structure also. But the thing is that you will study that topic in that course again. And we don't have much time here, only 11 weeks. So that's why I put a reason and then I removed that CO5 to make our contents less. Yeah. The main reason is we want to reduce our content. The main reason to remove that CO. But after this chapter 1, you will see some interesting things. And there is another topic in this chapter 1 that is called inference rules. I am thinking about them. According to the CO, there is no inference rules written anywhere. So I have that option that I can skip that topic. But that topic is very much interesting. Or you can say that topic is something important. So then I am thinking over it. I should have to go with that one or not. I am thinking over it. And my nature is, I am not happy with my own nature. I don't ever want to skip content. Whatever it is, either it is boring, good, or bad, or whatever, I don't want to skip anything if I am reading any book. If I am seeing any movie, I don't want to skip anything. I want to see all the details. Even the bad scenes? Yeah? Even the bad scenes? Whatever it is. Whatever it is, I want to see all the information. So this is what I am telling about my nature. So if you have the nature like that, then it would be very much difficult for you to complete something within some specified period. Anyhow, let's see what will happen. So this topic is negating quantified expressions. So negating quantified expressions. So now you will see some propositions in which the quantifier will be used, and you have to apply the negation over them. So now we will learn the concept of negation over these quantified expressions are statements in which you or we can use the quantifier. So for example, this is a statement. Every student in your class has taken a course in calculus. So from this word, every student, so you know that here the quantifier is universal. Here is the quantifier is universal. There is another quantifier. What is the name for that one? Existential. So you have to memorize these words. One is universal, which means for all devices. For example, you have the universal remote controller in the market. Why you are calling that? Because it is for it is for Samsung, it is for all other brands. Anyhow, so for every student in your class has taken a course in calculus. So it means that when you are going to convert this sentence into propositional logic, then the quantifier is universal. So you can represent this statement like that. For every x. So every student x in your class has taken a course in the calculus. And what is the predicate here? Taken a course. Yes, you can start from the verb, and verb is has. Okay, has is the verb. So you can start from here. Has taken a course in the calculus. So this is a sentence you can replace with P. And x is P of x. So this is something to represent the whole sentence. X is a student in your class which has taken a course in the calculus. Or you can simply say X is a student X has taken a course in the course in calculus. Anyhow, if this is the mathematical representation here, then you can say that what is Px? So then you can say Px is X has taken a course in the calculus. You don't have to write other sentences. If you are using this mathematical notation or propositional logic, then what you have to do? You have to explain what is X and what is Px, and then khalas. Okay. So here, that's why after writing it, then we are telling or we are informing that P of X is a statement. What is that statement? X has taken a course in the class. And this one is a universal quantifier for the variable X. And what is the negation? For negation, you can use the negation before this whole mathematical, like here, like that. So if this is the negation, now you have to solve the negation. So you have used the negation here. Negation for all x, P of x. And how you are representing negation from in chapter 1? I told you you can just introduce this before the sentence. It is not the case that, and then you can write every student in your class has taken a calculus. Every student in your class has taken a course in calculus. So you can introduce only this part before the sentence to represent negation. Or the other way is every student in your class has not taken a course in a calculus. This is the second approach to represent the meaning of the negation. So anyhow, so this is the mathematical, or you can say this is the notation, and this is something you can represent the negation in a sentence form. But you have to, how you can evaluate the negation? If there is a negation in the beginning of some mathematical statement, and if you want to evaluate that, the normal way to evaluate that is to move this negation symbol forward. If you will move it, the negation will go after this quantifiers. And quantifier, this is the variable x, and this is the quantifier which you are using with this variable. And the next part of this notation is P of x, starting from P of x. So then you can move this negation before that P of x. And when you will move this negation from here to the next portion of this notation or this mathematical equation, then this universal quantifier will be changed into existential quantifier. This will be changed according to some rule. And that rule is written here. We will see. When negation will move, then universal quantifier will be changed into existential. And then it would become there exists x negation p of x. Or you can say, which this was our starting with the negation. Negation for all of x p of x is logical equivalent to this part. This is what we are saying, that this is logical equivalent. This is the same thing. For example, if I am saying for all student and saying this is true, what is the negation? What would be the negation? If I am saying for all students, P is true, if I am saying, what is the truth? What is that? When this equation will be true? When I say for all students X, or you can say for all X, when P is true. And when it falls, not for all. There exists some student, there exists some X for which P of X is false. And here, this is what you are representing. There exists some X for which P of X is false. This negation means false. This is nothing else. So that's why these two statements, negation of for all of x, P of x is equal to logical equal to this one. If you will just focus on this, if you will just give more attention to these parts, left hand side and right hand side parts of this logical equivalence, then you will find that the meaning is same. The meaning is same. Did you get that or not? Just raise your hands. I don't know, maybe some student didn't get what. Don't raise it, Rashidi, forcefully. I know that you don't want to raise your hand. Allahu Akbar. Okay. So now this is example 2. So hopefully you will understand this thing again. What are the negations of statements, this one and this one? Two statements are given to you and it is asked to give the negation of these two statements. Okay, we are taking the first one now. We are considering first this statement for every x, x square greater than x. And what is the negation? You have to put negation before this statement, like here. Before its evaluation, you have to show the negation. And now what? Now you have to evaluate the negation. How you can evaluate? Move the negation forward. So that's why when you will move this negation symbol forward, then this universal quantifier will be automatically changed into existential. And the negation will come here at this position, before this portion, which is x square greater than x. So what is the negation of this x square greater than x? Negation means the opposite side. Okay, the opposite side. So what it is saying, if you have some x, if you are taking the square, that the value of that thing will always be greater than the value of x. And what is the opposite? When x square would be less than or equal to x. Would be less than or equal to x. So that's why now in the next step, what you can do, you can simply write it as there exists x, and you can remove the negation and you can write the opposite, which is representing the negation, which is representing the x square less than or equal to x. So now this portion is equivalent to this whole, this portion, which is giving the same meaning, because here you are writing something for that thing. Similarly, for the second part, This second part, there exists x square is equal to 2. Now this is the statement. Okay, put the negation symbol, move the negation symbol, then there exists will be converted to for every for every x negation x square is equal to 2. Now x square is equal to 2. What is the opposite? Not equal to 2. So that's why this is the next thing. So now in these two steps, you have shown the negation to these statements, and this is the answer. However, this last sentence is not needed anything. It is written something extra. Truth values of these statements depend on the domain. Okay, we don't have any domain values, so that's why he just mentioned the truth values of these two statements. If you want to calculate, it depends on the domain. Domain is not given to us. We have, so that's why we simply said what is the negation of these two statements. Here in the table, De Morgan's laws for quantifiers are mentioned. For quantifiers, if there is a negation like that, negation there exists p of x. What is the meaning of this one? The meaning the meaning of this negation is there exists x for which p of x is true. So this is the meaning without negation, okay? Without negation. If I am saying there exists x for which p of x is true, this is the meaning without negation. Again, there exists x for which p of x is true. There is one or more for which p of x is true. And what is the negation? What is the opposite of this? There exists one for which p of x is true. What is the opposite? For all. Not there is not one, but for all is opposite. For which p of x is, previously it was true, now it was false. So that is the way you have to think. So for every x, what is the now what is this statement representing? What is the meaning of this with negation? What is the meaning of this mathematical equation? Theoretically, for all x, p of x is false, which is written here. When is negation true? So when this negation will be true? When you have this for all x, p of x is false, then it means that this statement is what it is explaining, and then it will become true. Similarly, this statement which is written here, equivalent statement. So this statement is equal to this one, which is written here. So if you will move this negation forward, this existential quantifier will be converted into this for every x, and the negation will come here before the p of x. This rule is the rule which is called De Morgan law for quantifier, okay? So this is that you are changing. This is De Morgan law for quantifier. Okay, now think over it. What it is saying? It is saying for all x, p of x is, so previously, so if p of x, without negation, if p of x is true, you are making that true false with this negation. False with this negation. This is what it is saying. If there is no negation, then p of x means okay, that is true. But this negation is making it false. So for every x, p of x is false. So this is written here. Exactly. For every x, so this mathematical equation now you will understand completely. But it is equivalent to this one. And now there is another thing which is asked, when false. So when this negation will be false, it is not asked about this one. It is asked about when it will become true, this one, and when it will become false. Okay, it is written here. Here we are saying there exists. When it will be true, we already said where for all x, p of x is false. This is something which I discussed previously. And when it is true, there is an x for which p of x is true. There is an x for which p of x is true. Anyhow, read it by yourself. Only these things you have to understand, that this thing is equivalent to that thing, and this thing is equivalent to that thing. Allah Akbar. Example. You have this statement. For every x, p of x implies q of x, and you have this parenthesis starting and ending, and you have the negation here. And you have another statement, there exists x, p of x, and negation q of x. Show that these are logical equivalent. So you know that how you can prove a logical equivalent through truth table or through replacement of statement. So now in this example, we are going with the replacement of statement. So for every x, p of x, q of x, so we will start with this one, and we will replace the portion of this equation, and then you will get, if we will get this statement number 2 as a result, then we can finally say that they are logical equivalent. Anyhow, so just look over here. This is something P implies Q, according to our fundamental concept, according to conditions. So this is what it is written. If you will just ignore these x's, then it is P implies Q. And here you have the quantifier for all x, p of x is equal to q of x, and you have negation outside. Or you can say negation, and then you have these brackets here, and you have the implication. So if you will apply this concept of quantifiers to solve the negation, so this negation is outside. So what will happen if this negation will move forward? It will come here at this position. And then what? This universal will be changed into there exists x. And the negation will be here at this position. Allah. I have to show you those tables. Just a minute. So there exists x, and this negation will come here, which is like that. Negation, bracket starting, p of x implies q of x, and here the bracket is ending. And here the bracket is ending. So p of x implies q of x, and then you have the brackets around it. And negation is outside. So this is not something complicated written here. So what we have done here, we just moved the negation symbol forward. this universal will be converted into existential, and the negation is now here at its position. If you just remove these parentheses, then you will understand it completely, because this is what you have done here with the negation in this question. As you are doing things with this negation here in this question, from this portion to this portion, same you are doing here at this part. Same. But here you have the P of x and implies Q of x, which is written here. Starting from here, P of x implies Q of x, and this is the end of the bracket. And you have the negation outside. Okay. So now this is one step that you have performed, only you have moved the negation forward. Now you have negation P of x implies Q of x. So now we will do something. If you will look on the second statement of this question, then you have now this, there exists x now in your equation, but here you have P of x and negation Q of x, which you have the P of x and Q of x, but you don't have that negation with Q of x. You have to do some replacement, and then maybe it is possible. So you have to think over this portion. Negation into P of x and Q of x. And now we are using fifth logical equivalence in table 7 in section 1.3. So if you will just go into CO1, and if you will see those tables, Allah. So this is that slide. If I will press this button, which is for slideshow, then this whole screen will be shifted to that multimedia projector, and that becoming the reason that I'm not being able to record a video whenever I did this something. So that's why I'm not pressing this button. If I will press, then the screen will be blank in my recording, because now you can say that from this computer now the screen is shifted to the projector, not to this software Zoom. Anyhow, so this is the table 7, 1, 2, 3, 4, 5, and here you will see something. Maybe I don't know you are able to see that or not. Negation, P implies Q, logical equivalent to P and negation Q. Are you able to see that? Yes. So this is the form that we have here in that question. Negation, and we have P of x implies Q of x, logical equivalent to P of x, and negation Q of x. This is what we will do. But we are using this rule. Negation, P implies Q in a bracket or in parentheses, logical equivalent to P and negation Q. Okay. Now we are going back. And here you can see that negation P of x implies Q of x. This is that form. So you can convert it into what? P implies negation Q. So then what? P of x implies P of x conjunction. It was, what was? There was implication was converted into conjunction there. Okay. So if you have something like that, negation P implies Q, you can convert into the right hand side, which is given in that fifth rule, into what? P of x conjunction negation Q of x. So now, okay, convert this here, and what you will get, there exists x, P of x conjunction negation Q of x. And when you will get that, that is the second statement that you are getting now, and you have started from statement 1, and now you are approaching at statement number 2. And if you are getting statement number 2, even you have started from the statement number 1, then you can say that they are logical equivalent. It is written here. We have started from this statement 1, and where we have reached, after replacement of statements, we have reached at this statement number 2, here in this part. So that's why now you can say that these two statements are logical equivalent. Now, translating from English into logical expressions. This, by the way, translating from English to logical expression, this is mentioned in your COs. Predicates, quantifier to English sentences and vice versa. So that's why you have to go at least into these type of topics. Translate from English into logical expression, which means you have the English sentences, you have to convert it into some mathematical form. And for example, if you have expressed the statement, and this is the sentence, using predicates and quantifiers. What is this question is saying? That you have this sentence, you have to use predicates and quantifiers, and you have to convert this sentence into a mathematical form. So every student in this class, it means again universal quantifier. Every student in the class has studied calculus. So you can say, so this is just a discussion. Next, introduce a variable x, and for every student x in this class, x has studied calculus. Next, you can consider your sentence into this form. Or you can give this directly, and then you can say x is a variable for x is a student. Then you can say x is a student in the class. And what is C of x? You can say C of x is equal to x studied calculus. Because from this has x has studied calculus is this C of x. You can simply say, you don't have to write this whole detail. You can simply write this one, and then you can say what is x and what is C of x. And that is all you need. But here in this is the second portion. And here in this portion, it is explained that some students, not all, some students can think on this sentence differently, because every person can have its own concept. What is that concept? Maybe some student can think that first student will think that we have the people in the world, and then he will think that in the people we have the students in the class. It can come, it can happen, it can happen. So a student can think about what is the domain here in the class. So a student, any student in the class can think on this sentence differently. So for example, if some student is thinking first about the people and then about the student in the class, if it is happening, then what will happen? Then he will take this sentence, every student, that student will take this sentence like that. For every person X in the world, if that person X is a student in the class, then X has studied calculus. So now if some, so this is just a condition that maybe in the class one student is thinking in this way. In this way, he is thinking first about the people, and then in the people he is thinking about the students. Then the sentence would be in this form. For every person X, if person X is a student in the class, then X has studied calculus. And this portion of the sentence is if, then, which is what? Conditional statement, implication, arrow, if then portion. So then we can write this thing like that. Here you can say S of X implies C of X. And here X means if X is a student, then X has studied calculus. So this is representing this portion of the sentence. And for every person, you have for all X outside. So then this would be the mathematical representation if a student is thinking in this way. And it can also, and here in the last point, there is another situation is mentioned that if X has taken the calculus, for example, if X can take some other subjects also, not if he's taking Islamic studies, then it is not something that relevant with you. So then you have to change in your mathematical, you have to write calculus. So you will read it by yourself and you can understand it. It's not difficult. Using quantifiers and system specifications. This is again the example. Now here use predicates and quantifiers to express the system specifications. That specification is given to you into the form of sentences here. You have to convert those sentences again into mathematical form. So what is the first specification? Every mail message larger than 1 megabyte. Every mail message larger than 1 megabyte will be compressed. From every, you can understand, okay, you have to use universal. But every mail message, so mail message, you can take some variable X or M or what. For every mail message larger than 1 megabyte will be compressed. So look over here. I'm not going into details. So this universal for every, and this M is for mail message. Mail message larger than 1 megabyte. So here you are saying mail message M if it is larger than 1 megabyte. It is explained here what is SMY. So S is what is it? Mail message M larger than Y megabytes. So mail message M, you can change this S into L so that you can understand it better. Okay? So that you can understand this better. So you can change it into L. So for every M and that mail message larger than 1, okay, then it will be converted into compressed. Then it will be compressed. And then you can say, then M is compressed. So this is, here it is not if and then. So it's not easy to identify that here you have the implication, you have this arrow here. You have to identify from its meaning that the condition is there. And if the condition is there, then it is if and then. Yes. Okay. And similarly, if a user is active, so now it is if and then. So if a user is active, at least one network link will be available. So there exists, if a user is single user. So what it means, there exists some user U, and if U is active, it is the meaning. There exists some user, and if that user is active, then what? There exists some network N, and that network N would be available. Okay, and the discussion is written here. If when you will read, you will understand how it is going on. I am just making a shortcut. Otherwise, I can explain all these things. This is read it by yourself, and I will start here from this slide, inshallah, and next. And I will try to put the inference rules also. At the moment, inference rule is not the part of these slides, but I'm thinking over it, what I said in the beginning. And then maybe I will increase 4 or 5 slides more. Okay.